Hey guys, in this video we're going to be going over a quick review of conic sections, traces of 3D surfaces, cylinders, and surfaces of revolution. Just as a recap, remember that there are 4 distinct conic sections, each with different shapes and equations. So first off, we have circles. These are the simplest and you've probably encountered them before. They have the form shown below. Next up, we have ellipses, which are like circles except more general. These ones have the form shown below. Notice that if the a squared and b squared in this equation are the same, then you can multiply the entire equation by a squared and we get something that looks a bit similar to the formula of a circle. And this is true because circles are just ellipses where both sides are squished the same amount. If you stretch one side more than another side, you end up with an ellipse. That's how you distinguish the two. Next up, we have parabolas. You may recognize these ones from quadratic equations. They have the form shown below. And finally, we have hyperbolas. So, with these ones, you have to be a bit careful because their forms are very similar to ellipses. They have the form shown below over here, and you may notice that this looks very similar to the ellipsis equation. You have to notice that instead of a plus, where it would be in the ellipse equation, we have a minus instead here. So, you have to make sure to be careful with that, or else you might mistake the two for each other. Now, with that out of the way, let's review what the trace of a surface is with respect to a plane. When a 3D surface and a 2D plane intersect, we end up with a trace, basically the intersection, of the surface on that plane. When we want to find the trace of a surface on a certain plane, we just substitute the equation of the plane into the equation of the surface. This gives us the equation of the trace. For example, if we want to find the trace of the surface x plus y squared plus z cubed equals 2 on the plane x equals 1, simply substitute x equals 1 into our equation over here. In this case, after putting in x equals 1 in our equation, this will simply give us 1 plus y squared plus z cubed equals 2, which we can then simplify by subtracting 1 from both sides into y squared plus z cubed equals 1. This gives us the equation for our trace on the surface with regards to the plane x equals 1. Now, let's move on to cylinders. A cylinder is a collection of lines parallel to a given line that pass through a given curve along a plane. The lines themselves are called the rulings of the cylinder, while the curve the lines pass through is called the directrix. So you can think of cylinders as being generated by moving the directrix parallel to the given line, something like this. For now, we're going to be focusing on right cylinders. These cylinders have equations that involve at most 2 variables, so x and y, x and z, or y and z, but not all 3 at once. The variables of a right cylinder's equation tell us which axis its rulings are parallel to. If the cylinder is in terms of x and y, its rulings are parallel to z. If it's in terms of x and z, it's parallel to y. And if it's in terms of y and z, it's parallel to x. Basically, among x, y, and z, whichever variable is absent from the right cylinder's equation tells us the axis that it's parallel to. Finally, let's review surfaces of revolution. When you take a curve on a plane, so something that is at most expressed in 2 variables, like x and y and z, x and z, but not all 3, yet again, and you rotate it around a fixed line, you get a surface of revolution. This curve is called the generating curve, and this line is called the axis of revolution. We'll only be taking into consideration the cases where our axes of revolution are the x, y, and z axes. If our generating curve is in terms of x, so you can write it like y equals f of x or z equals f of x, our surface of revolution will end up being y squared plus z squared equals f of x squared. If our generating curve is in terms of y, like x equals f of y or z equals f of y, then our surface of revolution will end up being x squared plus z squared equals f of y squared. If our generating curve is in terms of z, like x equals f of z or y equals f of z, our surface of revolution will end up being x squared plus y squared equals f of z squared. Now, notice how, even though our generating curves are expressed in only 2 variables, when we rotate it around that line, we end up with a surface, a 3D surface, and so our surfaces of revolution all have equations of 3 variables. let's move on to some sample problems now. Okay, so we have our problem here. Consider the surface with equation 4x squared minus 9y squared plus 4z squared equals 36. We have this problem split up into 3 parts, which we're going to tackle one by one. The first part is to find the equation of the traces on the coordinate planes. So x equals 0, y equals 0, and z equals 0. And on the planes y equals negative 2 and y equals 2. Then, identify these traces. What kind of conic sections are they going to be? Second is to identify the surface and sketch the graphs using the traces obtained from the previous item. So what kind of surface are we going to get? Label important points on the traces with their coordinates. So these are going to be perhaps where they meet the axes or where they extend out to. Stuff that helps define the traces, helps us visualize what the graph is going to look like in 3D using these 2D slices that we've obtained. And third is find the inequation of the generating curve on the YZ plane if the surface is viewed as a surface of revolution. So, the first part of the problem asks us to find the equations of the traces on the coordinate planes and on the planes y equals negative 2 and y equals 2. Then, it asks us to identify these traces. What kind of conic sections are they going to be? If you remember, a while back, I told you that in order to find the trace of a surface relative to a plane, all we need to do is to substitute the equation of the plane into the equation of the surface. Let's start with the xy plane, shall we? Now, the xy plane is basically just given to us by the equation z equals 0. So, we just replace every z in our equation over here with 0. And so, after a bit of math, we get 4x squared minus 9y squared equals 36. Now, we can divide everything by 36 in this equation to give us x squared over 9 minus y squared over 4 equals 1. And we notice also that 9 is 3 squared and 4 is 2 squared, so we can rewrite those as 3 squared and 2 squared respectively. And look, we have something familiar here. We have an equation in the form x squared over a squared minus y squared over b squared equals 1. And looking back at the 4 conic sections, we see that this is in the form of a hyperbola. So the trace on the surface on the xy plane is a hyperbola. Now let's move on to the xz plane. Like before, we have that for the xz plane, the equation of this plane is y equals 0. So we just substitute y equals 0 into our equation, replace all the y's with zeros, and then we get 4x squared plus 4z squared equals 36. Now, we can divide everything by 4 in this equation, and we get x squared plus z squared equals 9. And once again, 9 equals 3 squared. So we have x squared plus z squared equals 3 squared. So this equation is in the form x squared plus z squared equals r squared, which is a circle. So the trace of the surface on the xz plane is a circle. Now let's move on to the yz plane. So the yz plane has the equation x equals 0. So once again, all we need to do is just put x equals 0 into our original equation, and we replace all the x's with zeros. This gives us negative 9y squared plus 4z squared equals 36. We can move the variables around again so that the z comes first, and we get 4z squared minus 9y squared equals 36, which is still the same equation. And now, once again, like with the xy plane, we divide everything by 36 to get z squared over 9 minus y squared over 4 equals 1. And once again, we know that 9 is 3 squared, and we know that 4 is 2 squared. So we can substitute those, and we get z squared over 3 squared minus y squared over 2 squared equals 1, which is very familiar because we've seen an equation like this before with the xy plane. And we know that this is in the form z squared over a squared minus y squared over b squared equals 1. And so we know that this is a hyperbola. So that does it for the 3 coordinate planes. How about we look at the planes y equals negative 2 and y equals 2. First of all, let's look at y equals negative 2. So once again, we just put y equals negative 2 into our equation from earlier. We replace all the y's with negative 2, and we get 4x squared minus 9 times negative 2 squared plus 4z squared equals 36. This gives us 4x squared minus 36 plus 4z squared equals 36. Now, we can add 36 to both sides to get rid of that negative 36 on the left side, so we get 4x squared plus 4z squared equals 72. We divide both sides by 4, and we get x squared plus z squared equals 18. And then, we know that 18 as a number is just the square root of 18 squared, right? We can simplify the square root of 18 to 3 times the square root of 2 if we want. But we now know that our equation for this trace is x squared plus z squared equals 3 times the square root of 2 all squared. Now this equation is of the form x squared plus z squared equals r squared. So the trace of the surface on the y equals negative 2 plane is a circle. So one last plane, we have y equals 2. So once again, we just substitute 2 for y in our equation. Put the plane into the equation of the surface. 4x squared minus 9 times positive 2 squared plus 4z squared equals 36. And so we get, once again, 4x squared minus 36 plus 4z squared equals 36. And we do the exact same thing here. 4x squared plus 4z squared equals 72. X squared plus z squared equals 18. And x squared plus z squared equals 3 times the square root of 2 squared. It's basically the exact same process as with the y equals negative 2 plane. So, because we know that the y equals negative 2 plane has the exact same trace as this one, we know that the trace of the surface of the y equals 2 plane is also a circle. So our second problem, the second part of our problem rather, is to identify the surface we're dealing with, what kind of 3D surface this is, and sketch the graph of this surface using the traces obtained from the previous item. We also have to label important points on the traces with their coordinates. Now, the equation of our surface is 4x squared minus 9y squared plus 4z squared equals 36. We can once again divide everything in the equation by 36 in order to give us x squared over 9 minus y squared over 4 plus z squared over 9. Now, we know that 9 and 4 are nice and square numbers, so we can replace 9 with 3 squared and 4 with 2 squared, and we put those in our equation. So we get x squared over 3 squared minus y squared over 2 squared plus z squared over 3 squared equals 1, which has the form x squared over a squared minus y squared over b squared plus z squared over c squared equals 1. This surface is a hyperboloid of one sheet, and we're going to be learning more about those and other kinds of 3D surfaces. They're called quadric surfaces in lecture number 20, topic number 20 rather. So if you want to know more about that, please check out that video. Anyway, from the previous item also, we got the traces of the surface with regards to 5 planes. The 3 coordinate planes and y equals negative 2 and then y equals positive 2. So, once again, we can also use those. We can draw these traces on the graph in 3D. And we're going to end up with something like this. But, well, okay. Of course, it doesn't make much sense to just go from having the traces to showing you all of them on the graph. There has to be some sort of process behind this, right? So, I'm just going to go walk you through how we reached this point. We're going to draw the traces one by one and label each coordinate point. Okay, now let's begin with the trace on the xy plane. It's a hyperbola with the equation x squared over 3 squared minus y squared over 2 squared equals 1. So, from this equation, we know 3 things. First of all, the center of the hyperbola. Now, we know that since the equation of a parabola is x minus h squared dot 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 and then y minus k squared dot dot dot, and in this case h and k are 0, we know that the center of the parabola is at the origin. Let's mark that down over here. Now, we also have the vertices of the parabola given to us by the denominator of the x squared term. In this case, the denominator of the x squared term is 3 squared, so we know that the vertices must lie on x equals positive and negative 3. Finally, we need to draw the guiding box so that our hyperbola has proper asymptotes. And so, in order to do that, we just look at the y squared term, the denominator of the y squared term, in fact. And we see that the denominator is 2 squared. We take the square root of that, and we see that the guiding box has to be 2 units wide in each direction. So we've had that drawn here. A guiding box with 2 units wide in each direction, and that stops at the vertices. We also have the center of the hyperbola over here at 0, 0, the origin. And that's enough information for us to draw it. And here we go. That's our first trace. Okay, let's move on to the xz plane. This trace has the equation x squared plus z squared equals 3 squared. And from before, we know this is a circle. Now, this circle has a radius 3. And we also know that like the xy plane trace, it is centered at the origin. So let's just draw that. We have the center at the origin. And because we know it has radius 3, we know that it must extend up to 3 units on each axis. So we draw that there. X equals negative positive 3, z equals negative positive 3. And just like before, this is enough information to draw our circle. We just connect the lines, connect the dots rather, and now we have the trace on the xz plane. Now let's look at this with relation to the xy plane. And you'll notice something peculiar, namely that at x equals positive and negative 3, the xz plane trace and the xy plane trace intersect. Now, these intersections will help us later to determine the shape, what it looks like, of the final surface. And so I want you to pay attention to these intersections, okay? See if you can figure out what the traces will sum up to look like for the final surface. Okay, let's move on to the yz plane. This plane has a trace that is also a hyperbola, much like the xy plane's trace, with equation z squared over 3 squared minus y squared over 2 squared equals 1. So, seeing that this is similar to the xy plane, we know that this also has a center of 0, 0, 0 at the origin. It has vertices at 3 and negative 3, but this time on the z-axis instead of the x-axis. And it also has a guiding box width of 2 along the y-axis. So, we just draw the vertices, the center, and the guiding box, and now we're ready to draw our hyperbola. Okay, now that we have our hyperbola, we're done with all 3 coordinate plane traces. Let's take a step back and look at what we have so far. And there it is. Now, you might be beginning to see the actual shape of the surface over here, the hyperboloid of one sheet I was talking about earlier. So let's continue a bit, and we'll see where we end up. Okay, so let's move on to our y equals negative 2 trace. We have x squared plus z squared equals 3 times the square root of negative 2 all squared. And okay, right, we have that the x and the z values of the center of the circle are at 0. But keep in mind, and this is really important, that this trace is on the plane y equals negative 2. So, unlike the xz plane trace, where the center of the circle was directly on the origin, the center of this circle must be somewhere where y is equal to negative 2. In this case, it's the points 0 and negative 2, 0 on the graph. And so the rest of the points on this circle must follow. They must have a y value equal to y equals negative 2 because they're on that plane. Now, we know that this circle has a radius of 3 times square root of 2, which is somewhere around slightly above 4. So we can draw those on the graph, and notice how all these points are on the y equals negative 2 plane, right? We can draw the circle, and I can label the points, and so we have the trace for the y equals negative 2 plane. And what does this look like in relation to the rest of the things we've drawn? It looks like this. Now, with all the traces on screen, it might get a little confusing as to what the shape exactly looks like, what the surface is. So I added a bunch of contour lines, and you can see that we've ended up with something resembling 1/2 of the funnel, a hyperbola of one sheet split in half. So we're almost done here. We can see the surface taking form, and there's one last trace we have to deal with, which is the y equals 2 trace. If you look at the trace, it's exactly the same as the y equals negative 2 trace, except this time, instead of all the points having to lie on y equals negative 2, all the points have to lie on y equals 2 instead. What this means is that we can just shift the circle we drew from the y equals negative 2 trace all the way so that we move it to y equals 2, that plane. And I've edited the important points here. I've labeled them to reflect this change. And that's our final trace. And now that we have this final trace, we can go back to the original picture and see how we ended up here with this hyperboloid of one sheet. Okay, the third and last part of our problem is to find an equation of a generating curve on the yz plane if the surface is viewed as a surface of revolution. So, our curve being on the yz plane, or the curve we're looking for being on the yz plane, is a fact that helps us narrow something down, you see. If the curve is on the yz plane, then we have two choices. Either we rotate the curve around the y-axis to get a surface, or we rotate the curve around the z-axis to get the surface. So we're going to need to look for if we can rewrite the equation in terms of x squared plus z squared equals f of y squared, or x squared plus y squared equals f of z squared. Something like those two forms that we were discussing earlier. So let's see. We already have a positive x squared term and a positive z squared term in our original equation, right? So we can just do nothing with those. In fact, we have a negative y squared term over here on the left side of our equation. So let's move that over to the right side, shall we? We move the y squared term over to the right side by adding 9y squared to both sides, giving us 4x squared plus 4z squared equals 36 plus 9y. Okay, now we have the x squared and z squared terms on the left side, and then we have a function in terms of y on the right side. Note that the function is in terms of y only. We're very, very close. All we need to do here is divide everything in this equation by 4. So we get our x squared plus z squared on the left side. So after dividing everything by 4 here, we get x squared plus z squared equals 36 plus 9y squared all over 4. Alright, so what we have here, we have x squared plus z squared equals, and then we treat the entire right side as one big f of y squared, right? And so we just take the square root and equate that to z, just like what we were discussing before with rotating something around the y-axis, right? We have z equals f of y. So we end up with two square roots, right? Positive and negative 36 plus 9y squared all over 4. And we can take either of those on the yz plane as generating curves of the surface. Okay, but you may be asking, how come we can't pick x equals the square root of this quantity, or x equals the negative square root of this quantity? Well, it's because we have the curve on the yz plane, right? And so, because it's on the yz plane, we must only have the curve in terms of y and z. If we have an x anywhere in this equation, then the curve won't be on the yz plane anymore, which means that it won't satisfy what the problem here is asking for. So if you see stuff like yz plane, xy plane, xz plane, normally curves on those planes are only going to be in terms of the two variables there. That's it for today's topic, and well, thank you for watching, and please do make sure to check out the other topics and the other videos on those topics if you want to learn more about the stuff I'm discussing, especially topic 20, which is going to go hand in hand with this one right here. Thank you.